Okay, so let's look at example 2. In this example, we are looking at the lock. This is the lock structure. This is very common practice. Once you have a canal, we need to just lock and block the water coming from different the ways of the sides of the canal. For example, from the left to right. If you have a different levels for whatever reason, for maintenance, for boating, shipping, everything, we need to just have like a sealed lock. And so this lock on the canal is sealed by a gate. So you can see we have like a gate here. It's like a 3 meters wide. This 3 meters wide is perpendicular to the plane, to the screen here. You can see it's like a 3 meters. Imagine it 3 meters perpendicular, like is the width of the gate. And it's perpendicular to the sides of the gates. So imagine we have a canal, and that's like a width is like a 3 meters. And here we know that when the lock is used, water depth on both sides are 3.5 meters on the left-hand side and 2 meters on the right-hand side. Okay, that's the assumption. So the question here is that what is the hydrostatic force of the two sides of the gate? So we just need to calculate the hydrostatic force. So here we can see the distribution of the pressure. The distribution of the pressure is something that we can just draw that one. Maybe it's not given in the problem, but you know that it's linearly increased, and its distribution is looks like a triangle distribution. For example, from the left-hand side, right-hand side, what you can see the magnitude of the left-hand side is like larger than the right-hand side because the depth is like higher. So that's like section 1. And section 2, at what height from the bed do the two forces act? So we need to just calculate the location exactly. Specifically in this figure, we need to just see what's the resultant force. Okay, if you have a resultant force left-hand side F1, what is its location? Or in other ways, let's see what is like a Y1. And for the right-hand side, if the resultant force is denoted by F2, what is the Y2? Okay. And for section C, we need, the question is that what is the magnitude of the overall resultant hydrostatic force on the gate? And what height does it act? So if I want to just convert both of them into one, how does it work? Let's see how we can just resolve this problem. For section 1, so it's very easy to calculate the hydrostatic force. We need to just see where is the centroid of the surface on each side, and easily calculate by using this formula, and need to just substitute the value in this formula, rho g at g times a. Okay, let's go and look at F1 first. F1, rho is the rho of the water, 1,000 kilogram per cubic meter, and g gravity acceleration 9.81 times hg is the centroid. Bear in mind, this is centroid. Centroid means on the left-hand side, imagine this like a rectangular, like a plane, and the centroid is exactly in the center of that. So 3.5 seconds, okay, this is like the left-hand side, times the area of the gate on the left-hand side is like the 3.5 meters high times 3 meters width. Okay, which is like the width of the gate. So once you're just gonna in this multiplication, the result is 180 times 26,000 newtons. Okay, this is like the force, and the unit is newtons or kilonewtons. You can say 1,000 newtons. And for F2, similarly, 1,000 times 9.81 times hg is a centroid, which is the half of the height, 2 seconds, which is 1 times 2 times 3. 2 is like the height, 3 is the width. Okay, 2 times 3, and the result is 58.86 thousand newtons. This is section 1. Okay, section 2, at what height from the bed do the two forces act? So that's simple. We're just gonna need, we don't need to just use that kind of like a general formula, because for triangle, we know that the center of the pressure or the resultant force acts 1/3 from the base or 2/3 from the top. If we want to just here calculate a third from the base, we can easily say, for example, based on this kind of like a distribution in this diagram triangle, a third for from the base on the left-hand side, y1 is a 3.5 third, which is 1.17 meters, okay, y1. And for y2 is like a 2 meters third, okay, or 2 meters divided by 3, which is equal to 0.67 meters. That's for section 2. Let's look at section C. What is the magnitude of the overall resultant hydrostatic force on the gates, and at what height does it act? So this is something a little bit tricky. You might need to just pay attention how it works. For example, in this case, we need to just look at how the system works in this case. That's just me. Sure, this one's here to show you how it works. For example, if you have like the gate situations like this one, imagine this is like this is the gate, and we have the resultant force on the right hand side. We call this one F2, and the left hand side is F1. So to calculate the overall force, so obviously the overall force will be the difference of F1 and F2, okay? So we're just gonna note that one by like the, let's say, right-hand side, which is going to be something on the left. So we can show that one here. I can call it FR, okay? But the way that we can calculate the resultant force is we can just use the moment regulations. So we're just gonna use the moment regulations for, first of all, to calculate the moment from the left and the moment from the right. Then the overall, if you're just going to calculate everything based on the general formula, the overall moment would be equal to the FR. So what does it work? If we want to just get the moment about point at the bottom, let's call it like the point O, the moment from the left hand side for F1, which will be like, for example, F1 times the depth or the lever arm. This is called lever arm. This is what we can call it F1, Y1. So F1 times Y1 will give us the moment on the left hand side. So I can just show it like here. This is I can call it M1. For the right hand side, let's just draw it with like a different color. So on the right hand side, I've got here the depth Y2. So Y2 times F2 will give me another like the moment on the other direction, so this direction. So I can call it M2. So, okay. So if you're just gonna say, okay, so you can just take the difference. M1 minus M2 will give me the resultant one. Obviously, I know the M1 is bigger than M2. So the M1, sorry, this one is M2. M1 minus M2 would be equal to the resultant one. I can call it MR. Okay, so let's say, let's go with like the red one. So MR should be in this direction. And the MR is equal to FR times the lever arm, YR. So let's like to have the lever arm is equal to this one. I can use this one. So by using these simple calculations, we can easily calculate. And so an MR and M2 are, all of them are really straightforward. You know, as I can just write here, M1 is F1 times Y1, and M2 is F2 times Y2. Okay, so if we're just going to substitute in this formula, for both. We can easily calculate MR, or we can substitute the MR in the top formula in here. You can easily calculate directly YR. What is the FR, by the way? FR, you can simply calculate FR is the difference of F1 minus F2. We already have F1 and F2. We can easily calculate FR, and then substituting in the below formula, we can easily calculate the Y1, YR. That this is the last one that we need to just calculate. Okay, so let's get back to the calculations here. Okay, so, and in other words, this is like the other way, by using the resultant force and overall force and location. The other like the way is that, you can see this distribution. If you can take away this distribution from the left-hand side, whatever left would be like the shape like this one on the left-hand side. In the tip of that kind of like the distribution has been taken off from or compensated from the right-hand side. So this is a trapezoidal like a shape. You can just calculate the centroid of this trapezoidal shape, will give us the resultant one will be the FR, and its location will be the YR. This is another way to calculate this one. But let's go with the calculation that we said by using the resultant forces, or take the moment about the resultant forces. So FR times lever arm YR is the way that we're just going to go to calculate that one to see what's the lightest for section C. So the overall resultant force is the difference of the F1 minus F2. So FR is 121.4 thousand newtons. Okay. To calculate the YR, we need to just take the moment, take moments about O at the bottom, the base, to find the height of the resultant, which is a YR. So based on whatever I've just written or handwritten in that kind of like the whiteboard, you can easily do this substituting that formula. This is like the overall force. On the right hand side is the difference of the moments, M1 minus M2, and on the left hand side is the moment of the MR, which is like the force 121.4 thousand times YR, the moment on the left hand side, and on the right hand side is the F1, which is the 180 times 26,000 times 1.17. This is the depth in here, left hand side, minus 58.86 thousand times 0.67, which is the Y2. Okay, why are you just going to put the minus figure, minus sign here? Because the direction of the M1 and M2 are in reverse. If you look at here again, MR, the moment, this FR Y1 applying to the right hand side, is like a clockwise direction, and M2 is the anti-clockwise direction. So obviously, if you want to just get the overall one based on the algebraic the relation, you need to just take the difference. So the difference of that is equal to the MR, or the resultant one, which is equal to the FR times YR. That's what we did here. So we're just going to use everything here, and this is what we have. So, and as a result of that, YR is equal to 1.41 meters above the bed. So this is the example to calculate the resultant force.